All right, as promised, we're going to take a look at a couple more examples. And specifically in these, we're going to tinker with a couple of different processes, ways that we can manipulate things or think about definite integrals and things like that. So again, more practice with general u-substitution. We're going to manipulate our integral to set things up right, specifically focusing on that differential du. And then we'll think about definite integrals under this context, this paradigm of variable substitution. So here we go. A nice starter example just to brush up on things. What I would encourage you to do is just pause the video right here and see if you can do this. Think about composition of functions. Think about products of with derivatives. Sorry, of inside things, all that kind of stuff. And if you can't get things started in like a couple of seconds after you pause and come back, I guess I'll maybe rewrite this out and give you a hint. So pause the video, give it a shot. All right, just as a hint here, what we're going to notice is that we can rewrite this as a product. And instead of dividing by x, I'm going to multiply by 1 over x dx, and hopefully that's a little bit helpful. So again, pause the video, see if you can finish this thing out. All right, our u-substitution. Hopefully we can see our inside part right here, natural log of x. And look at that. There's our derivative, right? So u equals natural log of x. du equals 1 over x dx. It's the derivative of that natural log times the differential dx. And now when we do our substitution, we end up with a secant squared of u now times du. The secant squared stayed because we didn't do any substitution there. But instead of having a natural log on the inside, we have u. This is great because we know the antiderivative of secant squared, right? It's our tangent function. So we have tangent of u plus our constant. But now we can go ahead and say, well, wait a second, u was natural log of x. So this is tangent of natural log of x plus c. Great. Let's take a look at another example. This one looks a little bit trickier, right? So again, if you need some help, I can help you find some composition and help set up the variable substitution a little bit in a couple of seconds, but pause the video and see if you can do this on your own. All right, if you're stuck on this, let me rewrite it for you. It's hard to see the composition, right? But maybe if I write things this way, it'll be a little bit easier. Ooh, look at that. That denominator is really in an exponent of -1. Why might that be helpful? And then the other hint is that we can always try and find that function derivative pairing. Pause the video and see if you can finish this out if you haven't. All right, if you have, here we go. Like you thought, we are going to say u is equal to 2x cubed plus 4x plus 1, and that makes du 6x squared plus 4 dx, right? So we're going to grab this and this. I'm going to combine those together and say that's du. So what are we left with? That exponent of -1. That's it. So we have u to the -1 du. You probably are going to think, oh, power rule. But wait, we know we're not allowed to do power rule on this because the exponent's -1. Okay, so write it again this way. I always recognize it a little bit easier when it's written this way. But either way, we know the antiderivative of u to the -1, or 1 over u. That's going to be the natural log function plus our constant of integration. And so again, we can do our little substitution back. Toss this 2x cubed back in place of u. We have the natural log of the absolute value of 2x cubed plus 4x plus 1. Oops, what am I doing? Plus c. There we go. Oh, on that note, actually, that brings up a good point. Sometimes students will ask me in classes, or they'll shoot me an email or message me or whatever, and they'll say, okay, I kind of understand u-substitution, but where did the du go, or the dx stuff? Specifically what they mean, though, is where did this part go? What happened to the 6x squared plus 4? Because normally when we think about just an integral, dx is just kind of like purely notational, right? It's like an end of an integral, and it tells us that we're going to be anti-differentiating with regard to x. But suddenly when we do a variable substitution, the differential du is more than that, right? It's like a whole expression. It's like a function. It's 6x squared plus 4. That's a thing. So what happened to that? Why is that just gone? What I will encourage you to think about is when you do the chain rule, where did that come from? If you were to differentiate natural log of 2x cubed plus 4x plus 1, where does that 6x squared plus 4 come from? Well, we just introduce it as the derivative of the inside, and we just multiply it in at the end. So doesn't it make sense that when we go backwards through the chain rule, we have to undo that multiplication and just kind of like get rid of it? We reverse that stuff. We put it back in place. It comes out of this inside part and gets multiplied in at the end. So when we do u-substitution for integration, we go ahead and we put it back. So it should make sense that it's not around at the end, since it gets introduced not arbitrarily during our differentiation, but it just kind of gets introduced seemingly out of nowhere. So that's where that goes. Okay, so those are our starter examples, but now we answer the what if question, right? Specifically, what if we changed our starter example that we just did to this? Okay, wait, how does this different? I don't remember. Oh yeah, look at that numerator, right? Didn't we change things? Let's go ahead and do the same sort of u-substitution. We're still going to pick this denominator as u because it's really in that exponent of -1. But now we'll notice we don't have a function and derivative pair because du is not 3x squared plus 2 dx. Du is supposed to be the derivative of u. So be careful. We don't really get to pick du. We're given that based on our choice of u. We picked u to be 2x cubed plus 4x plus 1. So that means du is 6x squared plus 4. And that's not in our integral, right? So what do? Well, maybe what you'll notice is that 3x squared plus 2 is connected to 6x squared plus 4, right? If you factor out a factor of 2 here, then look at that. Wow. This is in our integral, but we need a coefficient on this. So what can we do here? Well, I say just put the coefficient in place. You need a 2? Go ahead and put a 2 in there. But if you do that, you've suddenly just changed the whole integral, right? You've multiplied this by 2. So maybe what we'll do is try and come up with a nice process where we don't just arbitrarily change things, but we still end up with that coefficient of 2. And here's how we'll do it. We're going to multiply our integral by 1. Oh my goodness, that is revolutionary, right? If we multiply something by 1, what happens? Well, nothing. 1 is the multiplicative identity. But we're disguising 1 as 2 over 2. And the reason that we're doing that is so we can take this numerator and bring it inside our integral. We know that coefficients can pass in and out of our integral easily. That's one of our constant multiple rules of integrals, right? And so we're just going to take the 2 that we wanted and put it in place. So that works out nicely because now we can see u was 2x cubed plus 4x plus 1. And du, we said, was 6x squared plus 4, but we could write that as 2 times 3x squared plus 2 dx. And there it is. These two things together become du, and our denominator becomes u. Suddenly, this integral is half integral of 1 over u du. This is almost exactly the same as the one that we had earlier, except now we have this new coefficient of half out front, which should make sense. Our integral is half of the version that we did before because this here is half of the original numerator that we had, 6x squared plus 4. So this coefficient should make sense here. Okay, so now we can say half natural log of the absolute value of u plus c, and then we can do some substitution here, and that's half natural log of the absolute value of 2x cubed plus 4x plus 1 plus c. Everything works out great. You can do your differentiation to check this, and it's fine. Okay, but wait a second. What did we just do? Let's recap, just to make sure that we're not breaking anything, just to make sure that we're actually allowed to do this, and hopefully then we'll be able to come up with like some general ideas. What we've done is nothing, really. All we did was we multiplied our integral by 1. But we did that cleverly, right? We picked the version of 1 that we wanted. We used 2 over 2 because we knew we needed an extra coefficient of 2 in that numerator to make things match with our differential. I will go and I'll preface all of this stuff, maybe not preface because I'm saying this in the middle. I will make a note right now and say this is not the only way of thinking about this, and there's tons of other ways of learning this, and people will teach this differently, but this is one that I've always done. If we multiply by 1, we can move coefficients in and out of that integral easily with no problems, right? And so this only works because we're allowed to do that, which means this only works when our differential du is off by a coefficient. It doesn't work if our du is not matching up by with things by something else. And I'll show you what I mean a little bit later. In general, we can always fix our integrand coefficients if they're off, or our integrand functions, if they're off by coefficients. If we need some extra coefficient in there to find du or to form du, then we can do this however we'd like. So here's an example that we can do. We need to find the composition here to pick out what u is. Take a second to think about it, and hopefully we can see that, look at this, 4x minus 1 is wrapped up inside of these parentheses cubed, right? Really, the exponent on this is negative 3 because it's in the denominator. So we'll say, okay, u is equal to 4x minus 1. What's du? Du here is 4, the derivative of 4x minus 1, times dx. Now, we do not have an extra coefficient of 4. So what we can do is to just put it in there. But in doing that, we have to also divide by 4. Remember, what we've really done is we've said, let's multiply by 4 over 4, and then we'll take this and we'll put it in place. So we have 1/4 times the integral of 4 dx all over 4x minus 1 cubed, where we're going to take this stuff and make it u. Suddenly, this is our du. That's u. So we have 1/4 times the integral of du over u cubed. Again, like I said earlier, we can really rewrite this with a negative exponent. This is u to the negative 3 du. And now, again, this is just a power function. Add 1 to the exponent, divide by that value. Everything's going fine. So this is u to the negative 2 over negative 2 plus c. We've got negative 1/8 and then a u squared in the denominator, right? So negative 1 over 8 u squared plus c, which now we can say is, oops, we'll go black, so we're back with x, negative 1 over 8 times 4x minus 1 squared plus c. So again, we're just fixing this coefficient. What we'll notice is that if this was an integral of dx over 4x squared minus 1 cubed, this is what I was talking about earlier. I'll do the whole thing. U is 4x squared minus 1, and then du is 8x dx. So we can put the 8 in here, no problem, right? We'll multiply and divide at the same time. But what we can't do is this. We can't multiply and divide by x because x's can't move in and out of our integral when we're integrating with regard to x. That's not how things work. We can't peel that thing outside of our integral. And so this is not the method that we're going to be looking at here. If we have something like this where our du is missing but by more than just a coefficient, right? It's missing by like a whole function type. We don't even have that linear x in here. Then we got to do something else to figure this out. And there are some other strategies that we can do, right? We're not hopeless here. But u-substitution in this way is not going to work out nicely. We're going to have to come up with something else. Some of those methods are going to be saved for Calc 2 when we go through a whole bunch of integration methods. Some of those things is just going to be like fancy rewriting stuff and doing some other substitution or some other function type. And we can kind of explore those as we run into individual examples. But just be careful there. You can only do this with coefficients. All right, here's another example. This is a great one. Go ahead and try this. I always like these ones with the square roots floating around because it seems really crazy at first when you look at them. But give this a shot. All right, hopefully you'll notice, hey, look at that composition, right? Right inside that exponent. So let's say u is equal to the square root of x, and specifically we mean this one here. I'll show you what I mean there because I don't want us to write, oh, that's e to the u over u. That's not what we're doing. Because if this is x to the 1/2, then du is a half x to the negative half, or 1 over 2 root x. Oh, I forgot my differential dx. There we go. So notice this root x in the denominator is going to become part of my du. Maybe I'll rewrite this just so we can see what I'm doing here. But this is e to the square root x times 1 over square root x dx, where I'm saying this is u. And now you'll notice that what's really wrong is that I'm missing this extra coefficient of 2 in the denominator. So again, I'll write 2 over 2 on the outside. But now instead of peeling out the numerator version, I'm going to take the denominator version. I'm going to bring the half on the inside here. And I'm going to be left with, maybe I'll just do this. I'm going to be left with a 2 and a 2. This 2 is in the numerator. This one's in the denominator. And suddenly, all that stuff can become my du. So now my new integral is 2 times this integral of e to the u du. This is one of our nicest antiderivative functions because you just don't do anything, right? You just leave it the way that it is. And so this is really 2e to the root x plus c. If you wanted to check this, just do the chain rule on it, see what happens, multiply that out with that derivative of the inside, and it should work out fine. Cool. What about definite integrals? What do we do with these things? So let's take a look at definite integrals. Before we do this, I want to kind of go through this same sort of a picture that we have. So for definite integrals, our normal process is that we find an antiderivative function, but we don't stop there. What we do is we evaluate that antiderivative at a and b, right? And we said, oh no, sometimes this is hard. And that's where u-substitution comes in. So if you think about u-substitution, what we did before was this. We said, well, we took our function, we wrote it as an integral over here of g of u du from some u-substitution. And the point is that that should make this antiderivative easy. And then what we did was we brought that back over to x using our same sort of u-substitution. And you can do that. Once you have that antiderivative, you can bring things back over. But what I want us to also notice is that what these things are x values. This is really x equals a, and this is really x equals b. So if we do a substitution for a definite integral, let's come up with the corresponding u values here. We'll call them c and d. They're going to be different. You're going to plug these x values into the u substitution as well. And hopefully, if it's easy to find your antiderivative, then we just evaluate this at our new limits of integration. We use the fundamental theorem of calculus on this. So you can always take this path and translate back if you'd like, but it's more common and sometimes a lot easier and sometimes a little bit clearer if we just translate the limits of integration as well. I'll show you what I mean here, but this is kind of our new picture for our strategy. So, oh no, I've got a typo in these limits of integration. One of these is supposed to be something and one of them is supposed to be something else. Let's see. They were supposed to translate to 3 and 7. So if one of them translates to 3, that's going to be 1, and the one that translates to 7 is going to be 2. All right, let me change this. There we go. Fast moving stuff here. All right, this is supposed to be the integral from 1 to 2. Now, let's go ahead and do the u substitution on here. This is the same problem that we had earlier, right? So this is 4x minus 1 for u. Our du is again 4 dx, and oh no, we don't have the coefficient, so we'll put a 4 and a 1/4. They multiply to get 1, and we're just putting the 4 where we want it. Great, everything's working out fine there. Now we're going to do the u substitution, okay? So now this is where I want to focus on the fact that this is not x equals 1, it's x equals 2. And so when we have this u substitution of 4x minus 1 and du is 4 dx, and we still have these coefficients here, what we can do is take these values, we can still take these values, x equals 1 and x equals 2, and we're going to plug them in for x here, right? This u equals 4x minus 1. This is the key. This is the substitution method that we're going to do to translate this integral. So doesn't it make sense that we come up with corresponding u values here? So not only is 4 dx going to become du, and 4x minus 1 going to become u, so we're going to have this 1 over u cubed du. with a 1/4 coefficient, but now our limits of integration are going to change. The 1 is going to change to 4 times 1 minus 1. That's 3. So when we have x equals 1, that's going to change to u equals 4 times 1 minus 1. That's 3. And when we have x equals 2, that's going to change to u equals 4 times 2 minus 1. That's 7. So these are our new limits of integration here. So here's how we write this thing. It's 1/4, and again, this is in x equals 2 here. 1/4 the integral from u equals 3 up to u equals 7 of du over u cubed, which if you want to write it, you can write it this way. 1/4 integral of 3 to the 7, or to 7, sorry, u to the negative third du, and then our power rule comes into place. And remember, just so we have it later on, u is equal to 4x minus 1, and that meant that du is 4 dx. We're going to need that. All right, anti-differentiate. This is 1/4 times u to the negative 2 over negative 2. But now we're evaluating from 3 to 7. So we have negative 1/8 with a u squared in the denominator evaluated from 3 to 7. What we can do is just plug all this stuff in, do our fundamental theorem of calculus, right? This is negative 1 over 8 times 7 squared minus negative 1 over 8 times 3 squared. 7 squared is 49, so we have, I'm going to factor out the negative 1/8, and I'm going to say this is 1 over 49 minus, oh boy, maybe I won't. I'm going to get mixed up with all my algebra, or arithmetic, I mean. There we go. Minus negative 1 over 8 times 9. And this is just some nice arithmetic that we can crunch through, figure out what that actual value is. What you'll notice is that if we took our antiderivative and we converted things back using this u-substitution, we would have negative 1 over 8. But remember, instead of u squared, we could put 4x minus 1 squared. And then we could go ahead and do our evaluation from our x values 1 up to 2. And now you'll notice when you put 2 in place, you have negative 1 over 8 times 4 times 2 minus 1. There's 7 squared minus negative 1 over 8 times 4 times 1 minus 1. That's 3 squared. So notice it's the exact same thing. You just don't have to translate back to x if you take those limits of integration over. So in general, here's your summary. You can manipulate the integrand if you need to, right? Multiply coefficients wherever you'd like. Just make sure that you offset those by dividing by the same thing, right? Put that 1 on the outside of your integral, disguise it with, 4 over 4 or 2 over 2 or whatever you need, and then pull the pieces inside the integral when you need to. But you can only do that with coefficients, right? So don't do that with x's. The limits of integration need to be represented in the same variable as the integral, right? Notice when we're writing this as u equals 3 and u equals 7, that's because we have this du here. So definite integrals need to be written this way. You can think about what we're actually doing here. We're changing the heights of our functions when we change these functions here, right? We're changing what the thing that defines the height of that curve is. And when we change the limits of integration, we're changing the width correspondingly. So if you think about area under a curve, you can think that what we're really doing is just manipulating the shape of it, but keeping the area consistent. And whenever we stretch the height by something, we stretch the width by a corresponding factor. And you can kind of think of that in the opposite. There's lots of pictures that you can find online or in the text that show this. But this manipulation of the area, what we're saying is that if we change the function, the actual thing that's defining the curve, that will obviously change the area. So we have to change the width part, the limits of integration, correspondingly. And if we use the u-substitution, then that'll make sure that the areas are going to be the same. So that's what we've got. Hopefully that's helpful to see. Good luck as we go through integration stuff. We have one more u-substitution video to talk about with turnaround problems, and that will be another fun thing to do.